All right, welcome everybody. This is the first lesson on Precalculus with me, Farhad Gujari. I'm super excited to teach this course and create the videos for it. I've been teaching this class for a while, and now I get to make the playlist and the videos for it. So I'm super excited. So this will be the first video, and if it's your first time as my student or first time watching my videos, I'll just talk about my teaching style while I'm going through the videos, so you can carefully see what you need to do to be successful in this course. So here, my teaching style and just some notes and ideas. First, always write your notes neatly and carefully. When I was an undergraduate student and a graduate student, I even wrote my notes over twice. You don't need to be that OCD or meticulous, but it really does help. Okay. There will be times when I'm going through the video and I'll say, hey, pause the video. And when I say that, I would really like you to pause the video and think about the problem or the question I'm asking and try and complete the problem on your own. Skipping ahead without trying to do the work won't help, right? Even if you fail miserably at what you think the correct answer will be or how do you solve this certain problem, going through that process of pain and getting those mistakes will benefit you a lot. And if you think you just skip through it just because you want to see the answer right away, it won't help you as much. Trust me on that. While you're using your notes and writing your notes, please use colors. Your notes will pop up and it'll look much nicer. And really, after each video, take a few minutes to read and go over your notes. It's really nice to always summarize just a little bit. And if you ever feel lost or confused within the video, just let me know in the comment section. And if I ever make a mistake, let me know as well. I'm a human being. All right. So yeah, let's do this. Let's enjoy the show. So here, Precalculus, lesson number 1. So before we actually jump into the lesson, the question is, what is Precalculus? Right? So here, basically when we're learning calculus, we're just learning the skills needed for calculus. And I will explain very soon what calculus entitles, right? So the topics that we'll cover are functions and their graphs, exponential and logarithmic functions, applications of trigonometry, sequences, series, probabilities, matrices, and some other topics, right? So right now, maybe you have some familiarity with these topics, maybe you don't, but I'll do my best to explain each topic, right? All right. So now the big question is, what is calculus? So here, calculus can be broken into two main branches. You have differential calculus and integral calculus. So within differential calculus, the derivative of a function can be geometrically shown. I'll show you on the next page. Actually, wait, yeah, let me just show you on the next page here. Here, the two main ideas within calculus that we want to prepare for are derivatives and integrals. And the idea within a derivative, you're finding the instantaneous rate of change or the slope of a tangent line at a particular point. And if you're like, Professor, I have no idea what the hell you're talking about, it's okay. The idea of this course is to get to this topic within derivatives, and the other major branch are integrals, where you're finding areas under curves. Okay. All right, let's do it. So here, the first topic that I want us to make sure we're solid with are the types of numbers that exist. So here, like if I were to say, hey, what is a natural number? What is an integer? What does it mean for a number to be rational or irrational? What does it mean for a number to be real or complex? If I said, hey, pause the video and honestly think of a proper definition for all these types of numbers, or what you think each definition is on your own, could you really do that, right? And what we'll do is, in the first lesson, we'll just go over these ideas of these types of numbers, and then we'll continue on, right? So first, what I'd like you to do is just have this in your notes. Anytime we talk about, and if you want, yeah, pause the video, right? Pause the video, have this in your notes. We'll say that a set is a collection of objects, and those objects are called elements. A set encloses a list of elements by braces. So for example, if I have my set A, and the braces over here kind of encompass everything what's inside my set, the elements are the items within my set, right? And now here you might be thinking blah, 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 blah. So let me show you a nice little example, nothing too crazy. I like basketball. So if I said, let my set be called the NBA, here's my set. This is NBA. And we're going to say that within the NBA, you have teams, right? You have the Knicks, who I love, but are also terrible all the time. You have the Lakers, you have the Heat. Here are the elements within this set. And notice that I could kind of keep going with other teams within the NBA, and I could close it with the braces. If you want, I could say, let's create a set J. And let's say set J means foods. Okay, so what are some foods you like? You could say pasta, rice, chicken, whatever you want. And within this set J, the elements within set J are the foods that I want to put in my set. And then the braces kind of hold everything in there. And when I have this, we call this an ellipsis. Here we're saying that some sort of pattern continues, and the pattern of types of foods can continue within this set. And that's the idea of a set. And notice that what we're going to show are the sets of these types of numbers. This encompasses a set of the natural numbers, the set of integers, the set of rational, irrational, real, and complex. And we're going to go over these sets of numbers. Okay. Side note, elements within a set are never need repeated. So like for example, if I have my set over here, I don't need to write pasta again within my set because I already have pasta. You don't need to repeat any elements, and elements are separated with a comma. So here, that idea that anytime you have a comma, it separates the element within the set. Cool. Okay. So let's intro it, right? Here, the first set of numbers that we need to be solid with are natural numbers. So let me zoom in a little bit, get a good camera angle. Very nice, okay? So if I said, hey, pause the video, what does it mean for a number to be natural, right? What do you think it'll be, right? Here, the set of natural numbers will be the counting numbers. So think of the first natural number you have is 1, 2, 3, 4, 5. And here we have this ellipsis over here that implies that the pattern continues. So it's 6, 7, 8. These are just positive whole numbers. Positive whole numbers. That is a set of natural numbers, right? And then here we could say that 0 is not a natural number. And the set, like over here, when we had the name of the set, NBA showed my NBA teams, this set J showed the foods I liked. Anytime you see this symbol, capital N, like this implies that this set are my natural numbers over here. Okay, this is you have to know this symbol. This symbol means natural numbers. Fantastic. Okay, so we did the first set. Let's look at the next set. Here, whole numbers. If I said, hey, pause the video, what does it mean for a number to be whole? What would it be in your own words, right? Try and pause the video and think about that for a second. Here, what does it mean to be a whole number? Basically, it's all the natural numbers, including 0. That's it. And notice that negative numbers are not here. So then here, basically natural numbers with 0 included. Fantastic. And here, I forgot, I'm not really sure if there's a symbol notation for whole numbers. I don't remember. But okay, let's keep going. Next setup. Oh crap, I should not have showed you that. What does it mean to be an integer, right? Pause the video and hopefully you didn't peek at that, but what does it mean for a number to be an integer, right? And here the idea is that to be an integer, you are the natural numbers, you're also 0. So notice that you have all the whole numbers, right? And you also have all the whole negative numbers as well. So like you have 0, 1, 2, 3, 4, 5, 6, 7. Those are all integers. And then you have -1, -2, -3, -4, la 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 la. So the integers basically encompass the negative numbers as well, but whole, right? Okay. And here, here's a nice little visual for you. You just have this number line, right? So here are the integers. So basically you have negative integers, 0, positive integers, right? And the symbol for integers is this Z looking symbol, okay? This symbol will show integers. Fantastic. Okay, let's continue. Here, the next set of numbers are the rationals. So what does it mean for a number to be rational? This is probably the toughest one. This one will take a little bit of explaining. But if I said, hey, pause the video, what does it mean for a number to be rational? Try and create your best definition. Okay? All right, here it is. Here, we're going to say that a number is rational if it is the quotient of two integers, sum a over b, where a and b, and this symbol means are inside the set of integers. And our b value cannot be 0 because you're not allowed to divide by 0, right? So just to review this definition, a number is rational if you could express it as some integer over integer. So basically, my integers have to be in this set, right? So I have some whole number, whether it's negative or positive, divided by some value of b, right? Okay, and that's what it is. So here, what are some examples? We could say, let's take a look. 2 over 3, I have integer over integer, integer over integer, integer over integer. These are all rational numbers, okay? Now here, let's take a look at this question over here that is a good one. If I said, hey, are the numbers 5 and -3, are these rational numbers? Pause the video and think about it. If these two numbers were rational, then you could express 5 as some a over b, and you could also express -3 as some a over b, where my a and b are integers. And can you do that? Okay, let's take a look. The answer is yes, you can, because I could just say 5 is 5 over 1, and notice I have integer over integer. So notice that this number 5 is a natural number, it's a whole number, it's an integer, and it's a rational number. Okay, so you'll notice that there are some numbers that are inside multiple sets. And the same idea as -3. I could express -3 as -3 over 1. So this -3 and 5 are also rational numbers. Okay, let's continue. Rational numbers are also numbers that are in decimal notation, and they could have some sort of terminating pattern or a repeating pattern. So what do I mean by terminating and repeating? This number over here, 6.25, just terminates at 5, right? Like I could just show this as 0, 0, 0, 0, right? So notice that the pattern just stops. So this number over here is 0.625 is a rational number. And also, if you have some sort of decimal and some sort of repeating pattern, like 0.363636 la 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 la, then this number is also rational. But then the question we need to ask ourselves is, if they are rational, right? If this number is rational and this number is rational, then you have to be able to express this number as some a over b, where a and b are integers. Like if you're going to say that this number is rational, you have to be able to show that somehow, some way, some integer divided by another integer gives me this number. Okay? And what will be that number? Let's look at some magic. Let's take a look. Aha! So now notice that 0.625 can be described as 5 over 8. Because you know that 5 over 8 is rational just by looking at it, right? Because you have integer over integer. So if 5 over 8 is rational, then 0.625 is also rational. Okay, let's take a look at this one. If I'm saying 0.363636 is rational, then there has to be some a over b that does it. So let's take a look at this. Mwahahaha. Right? So notice that if I take 4 over 11, and 4 over 11 is rational, and it feels okay that it's rational for you because it's very easy to see that it's some integer over integer. And if 4 over 11 is rational, then that decimal notation of what you get for 4 divided by 11, this number is also rational. And notice that what does this bar mean over here? That the pattern repeats of 36, 36, 36, 36. It keeps going. Okay? Muy bien. All right. So that is the idea of a number being rational, right? It has to be some a over b. And notice that if you have numbers that are if you have decimal notations that are in terminating or repeating patterns, then those numbers are also rational. So here, let's take a look. Here are examples of terminating and repeating patterns. And every rational number can be written as a repeating decimal or terminating decimal. Okay? Now the notation or the set of rational numbers is this Q with the line kind of to the left side of it. And this is the symbol for the set of rational numbers. So you have these three very, very nice symbols so far. We have N, like this. You have Z, like this. And you have Q, like this. These are my naturals, these are my integers, and here are my rationals. These are three very, very important symbols for you to have in your set of math skills. Okay? Now here, so far, so good. We've talked about natural numbers, integers, rational. Now this is the best definition. What does it mean for a number to be irrational? This is a tough one. But in all honesty, all it means for it to be irrational, it basically means not rational. So the idea of not rational implies that numbers that cannot be written as a repeating decimal or some terminating decimal, these numbers are irrational. Okay? Now use your math skills that you have. Can you think of examples of numbers that are irrational? All right, pause the video. Square root of 2. Because this pattern of 1.141213, it doesn't have a repeating pattern that exists. The numbers are random. The same idea with pi, 3.141592 la 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 la. The numbers don't have a repeating pattern. So this number is irrational. This number is irrational. This random number here, 45455, 45555, la 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 la. This does not have a repeating pattern, thus these are examples of irrational numbers. Okay, fantastic. Almost done, almost done, almost done. And now here, the final set for today are real numbers. What does it mean to be a real number? It means you're on the number line. So basically, the set of real numbers are the union of all rational and irrational numbers. So any number on the number line is a real number. So I could have 0, 1, 2, 3, -1, -2, -3, right? I could also have square root 2 is over here. Notice that's some irrational number. I could have 1/2, which is over here. That's a rational number. So basically, to be a real number, you're putting the set of rational and irrational numbers together. And that's what it means to be on the number line. And here is the notation to be a real number. This is the set of real numbers. So let's do some examples of what does it mean to be a real number. Sorry. You have 0. Oh, let me zoom out a little bit. Okay. You have 0, 1, 3 over 4, square root 2 over 3, pi over 4. All these numbers are here. What are some examples of numbers that are not here, that we haven't discussed about yet? Pause the video and think about it. What numbers or ideas will not be here? Okay. 1 over 0. This is undefined. You're not allowed to do that. Infinity is not even a number. It's an idea. Square root -1. And if you remember something you may have learned in the past, this value is I. And the final set of numbers that we did not talk about are complex numbers. And this has to do with this I equals square root -1, but we're going to do that for another day. All right, everybody. That is it. What I'd like you to do, review your notes, make sure you have a good understanding of your sets of numbers, and I'll create some sort of problem set where you get to practice the ideas of where to put these numbers in certain sets. All right. I'll see you in the next video. Great job.